Hello viewers. So in this video, we're going to look at chemical kinetics multiple choice questions review. So we're going to review about 10 questions in this video. So let's start with the first one. The first one is saying for a reaction, the rate law is rate is equal to. So we're given the rate law and they're saying what is the overall order of the reaction. Now, the rate law we're given is rate is equal to K multiplied by the concentration of A, which is multiplied by the concentration of B given to the second power. Now let's interpret what we have here. What we have here is this concentration of A. This chemical reaction has reactants A and B. So the order of reaction according to reactant A is first order. This A we have here without a power shown there. Each power is 1. When the power is 1, we don't need to show that. And then the order of reaction according to reactant B is second order, which is 2. So in order to get the overall order of the reaction, we need to basically add the orders of reactants we have. So we have first order for A and we have second order for B. So to get the overall, we'll say what we have is 2 added to 1, which is giving us 3. So this implies to say the order of reaction is third order. That's the overall order of reaction. So our answer in this case is C. So that's it for the first question. Let's go to the next one. So this one is saying the half-life of a first order reaction is 30 minutes. How much of the reactant remains after 90 minutes? So the information we have is T half is equal to 30 minutes. So this is our half-life. And then the total time we are given is 90 minutes. So total time is equal to 90 minutes. All right. So to find the number of half-lives that we have in 90 minutes, remember we need to determine the number of half-lives we have in 90 minutes in order for us to know how much will remain after that 90 minutes. So to get the number of half-lives, we are going to say we'll have the 90 minutes, which is the total time, divided by 30 minutes, which is the half-life. So when we do this, we're going to find to say we have 3 half-lives in this 90 minutes. After doing that, we can now use this formula that says 1 over 2 given to the power of n, where the n is the number of half-lives. And this will give us 1 over 2 to the power of 3. And when you multiply half by half by half, what you're going to get is 1 over 8. So our answer here is 1 over 8. In this case, again, we have our answer to be C. The other method you can use to find the amount that remains after 90 minutes is using this method. So you say what you have, you're starting with 1. So initially, the amount you have is 1 in this case, and then you have 3 half-lives. So you say the one you have, which is the initial amount, you get its half amount, meaning you are multiplying by 1 over 2. And this one will give us 1 over 2 for the first half-life. So this is for the first half-life. What this implies is after the first half-life, we're going to remain with half of the initial amount. And then for the second half-life, we are starting with what remained, which is 1 over 2, and we are still getting half of that, and we'll say we're multiplying it by half. This will give us 1 over 4. This is for the second half-life. And then after that, since we have 3 half-lives, we'll go and find what will remain after the third half-life. So now we have 1 over 4 remaining after the second half-life. we get half of 1 over 4. That means we multiply by half. This will be equal to 1 over 8. So this is for the third half-life. So clearly we can see what remains after the third half-life. What remains is 1 over 8, which is the same thing we got on the other side. So our answer is C in this case again. So that's it for this question. Let's see what is next. What are the units of the rate constant for a zero-order reaction? So in this case, we are looking for the units of the rate constant for a zero-order reaction. So how do we find those units? To find the units, the formula you need is this. M, this is capital M, representing molar concentration to the power of 1 minus N, then divided by S. So this is the formula you need to find the units for the rate constant for any order of reaction. It can be 0, it can be first, it can be second. You need this formula here. Where in this formula, this N we have is the order of reaction, the overall order of reaction, N in this case. So let's find the units for a zero order. So this will be equal to what we have there is M on top, then 1 minus 0. We replace the N by the order of reaction we are dealing with. So in this case, we have a 0. So this will give us 1 minus 0 is 2, 1. So we have M to the power of 1 divided by S. Now when the power is 1, we don't need to show it. So this will be M over S. Yes, so this can also be represented as M, then S to minus 1. So these here are the units of the zero order rate constant. But then in this case, this type of units is not what is represented in our multiple choice there. So it's not the format that we have used there. So let's change this format we have here to the format that we have in the multiple choice. How do we do that? Now remember, the M we have on top there is molar concentration. So using this one here, we'll say the molar concentration on top is moles per liter. So we replace it by moles per liter like this. This is what we have on top. And then this is divided by S down there. So we have S down there. And this will just be moles over liter. We introduce the multiplication sign. It means we need to switch the denominator and the numerator on the other side. So this is like over 1. And now here it will be 1 over S. So this will just give us on the other side, we'll have moles per liter, that is multiplying by seconds like that. So these are the units we have for a zero order reaction. Just putting them now as they are there, this is the same as moles. So we'll have moles on top. When we take liters on top, the liter will be minus 1 and also the S will be minus 1, which is now our final answer in this case. Moles multiplied by liter to minus 1 and multiplied by S to minus 1. If we are wondering where this is coming from, where the minus 1 and minus 1 are coming from, is from the concept of indices. If you have 1 over x, this is the same as x to minus 1. Yes. So if you have 1 over L, this is the same as L to minus 1. If you have 1 over S, this is the same as S to minus 1. So this is why you are seeing this L here is down. So it's like 1 over L. And when you take it on top, this is L to minus 1. The same applies to the S. That's why we have S to minus 1. So this is our answer here. And looking at the choices we are given here, this answer matches B. So our answer for this question is B, like that. That's our correct option. So let's see, just for the sake of more understanding, let's also find the units for a first order chemical reaction. So let's say this question was asking us to find for the first order instead of zero order. Using the same method, this was going to be equal to M, then we have 1 minus 1. Since it's first order, we'll replace the N by 1, then divided by S. Now this is equal to M. 1 minus 1 is 0, and this will be divided by S. Anything given to the power of 0 is 1, so what we have on top is 1 divided by S. And this is just the same as S to minus 1, or per second. So if we're looking for the units of the rate constant for a first order chemical reaction, our answer in this case is S to minus 1. In this case, we're going to have it as, this is A. Yes, S to minus 1 is option A, like that. So our answer was going to be option A. Let's look at the other one where we are saying if we are told to find for a second order reaction. So for a second order, we're going to say this is M 1 minus 2, then this is divided by S. This is going to give us M, then 1 minus 2 is minus 1 divided by S. And this was going to give us M to minus 1, then S to minus 1. Taking these units in the format we are given here, what we do is, on top there, M minus 1 is the same as 1 over M. So we'll have 1 over M like this, and then this is divided by S. Doing our mathematics there, we're going to say we have 1 over the M we have down there is molar concentration and is given by moles per liter. So moles per liter and everything is being divided by S. So when we reach here, we're going to say, let's first solve what we have on the left-hand side before we involve the right-hand side, like that. So let's do that. We're going to say what we have is 1 that is being divided by moles per liter, like this. And this is going to give us 1 that is being multiplied by the liter will go on top and the mole will come down. And this is just giving us liters per mole, like that. So this implies to say this is what we have here. The final answer on this side alone is liter per mole. Then that's what we are now bringing in here to say, okay, we have liter per mole that is being now divided by S. Yes, let me just write that properly. Divided by S, like that. Now let's take this part on this side here. So let's work it there. We're going to say we have liter per mole. That is now multiplying by, we're going to say now we have 1 over S, and this will give us liters over mole. That is multiplying by S, like that. When we take this on top, this is going to be equal to, we have liters, then we have moles to minus 1, and then we have seconds to minus 1. So these were going to be the units if we're looking for the units of the rate constant for second order chemical reaction. In this case, our answer was going to be this one here, you can see here. So C, option C was going to be our correct answer if we're looking for the second order rate constant units, like that. The next question is saying, for a reaction A giving us products, the plot of natural log of A base time gives a straight line. What is the order of reaction? So we're looking for the order of reaction. The question is saying what is the order? We are basically looking for the order of reaction. Is it the first order, second order, zero order, or third order? So let's go ahead and see how we can determine that. Now this is determined from the integrated rate laws. The integrated rate law that is containing natural log of A is a first order. is given by natural log of A. The concentration of A in that format is equal to minus KT, that is being added to natural log of A initially. So this is the integrated rate law for a first order chemical reaction. For a zero order, we have the concentration of A at the final stage is equal to minus KT added to the concentration of A initially. And then for a second order, we have 1 over the concentration of A to be equal to KT added to 1 over the concentration of A initially. If any of those gives you a straight line, it means that's the order of reaction we have. So in this case, our answer is B, is first order. So that's what we have for that one. Let's move to the next one. Which factor does not affect the rate of a reaction? A, temperature, B, concentration, C, catalyst, and D, we have delta G, which is Gibbs free energy. So now, temperature affects the rate of reaction. Remember, if you increase temperature, the kinetic energy of particles also increase. If you reduce temperature, the kinetic energy of particles also reduce. So temperature affects the rate of a chemical reaction. Concentration also does. A catalyst also does affect the rate of reaction, but Gibbs free energy does not affect. So what we have here is D is our answer. Gibbs free energy show us if a chemical reaction is spontaneous or non-spontaneous. Yes. All right, so that's it for that one. Let's move to the next one. The activation energy of a reaction can be determined from, so we're given options there, the rate constant at one temperature, rate constants at two different temperatures, initial concentrations only, and then we have half-life only. So the answer for this one is B. The activation energy is mostly used or calculated using Arrhenius equation at two different temperatures. Yes, mostly we use natural log of K2 over K1. It can be K1 over K2, still the same. We'll have activation energy on top there divided by R, and this is multiplying by 1 over the first temperature minus 1 over the second temperature, like that. So this is the formula that we mostly use to calculate the activation energy. So our answer in this case is B, because we're talking about the rate constants at different temperatures. We have K2, K1, we also have T1 and T2. So that's our accurate answer in this question. Let's move to the next one. For a second order reaction, the plot of dash versus time gives a straight line. So we have A, the concentration of A. This is not correct because this is found in the zero order integrated rate law. So we plot the concentration of A against time if it's a zero order to check if it will give us a straight line. Then we also plot natural log of A, the concentration of A, if it's first order. And then we plot 1 over the concentration of A if it's second order. So this is our answer that we have here. C is our answer. The half-life of a second order reaction increases with increasing initial concentration, decreases with increasing initial concentration, is independent of initial concentration, is constant for all concentrations. Now the half-life of second order is given by T half is equal to 1 over K multiplying by the concentration of A initially. This is what we have for a second order chemical reaction as our T half or our half-life formula. So we're comparing our half-life and the initial concentration. What is the relationship between these two? Now, since this is down here, it implies to say these two are inversely related to each other. The relationship is inverse. What that means is when you increase the concentration of A, T half is going to reduce. And when you reduce the concentration of A, T half is going to increase. So they are inversely proportional to each other. So it implies to say the correct answer here must be that which is showing to say when this one increases, the other one reduces. On our options here, the first one is increases with increasing initial concentration. That's not correct because this shows that those two are directly proportional to each other, which is not correct in this case. It increases with increasing initial concentration. Yes, this is correct because it shows to say when one is increasing, the other one reduces. So our answer in this case is B. So yeah, that's our answer. According to collision theory, which factor determines whether a collision is effective? A, we have energy only. B, we have orientation only. C, we have both energy and orientation. And D, we have frequency only. So for the collision theory, to have effective collisions, we need to have the right orientation. But then for these particles to move and collide with each other, we still need to have energy that is going to help them move. Energy in form of kinetic energy due to movement. So this implies to say in order for us to have collisions that are effective, we need to have both energy and the correct orientation. So this gives our option C to be the best option. In the Arrhenius equation, K is equal to A, E to the power of. So what we are given there is we have K, which is equal to A, E given to the power of minus the activation energy that is dividing by RT. And then what does A represent? So the A we're talking about is this one here. What does this A represent in this equation? So this one is called the pre-exponential factor, or rather the frequency factor. So it's either you call it the pre-exponential factor or the frequency factor. So if you see this one and you are looking for what A represents, this will be correct. If you see the frequency factor, again, that will still be correct. So according to what we have here, the correct answer is B. Yeah, B is the one that is holding the frequency factor. So B becomes our answer automatically here. It's not the rate constant, it's not gas constant, it's not activation energy, but it is the frequency factor. Activation energy is the EA on top there. The rate constant is this K we have here. R is the ideal gas constant, which is the gas constant we're being told here on T, and T is temperature. So this is the frequency factor. So that's it for this video.